So for basic error analysis, you have to first differentiate the difference between accuracy and precision. So what you have here is four targets, four maybe dartboards. Or sa mga estudyante ni Ma'am Gamag, you had some activity last December doing like this. So probably some of you perform like this, wherein the dots are the points where you hit the paper when you did your archery activity. Some of you maybe did this. I don't know if you have, yeah, some of you did this kind of targets, especially this one. So when you say accuracy and precision are entirely different things. Okay? So if you're going to look at these four illustrations, you will see that some of these are highly accurate, or maybe the archer is highly accurate but less precise. Some of this describes an archer who is imprecise but accurate. Some of them will be accurate and precise. Some of them is neither accurate nor precise. Okay, so for letter A, as you might predicted, this figure shows an inaccurate archery and also an imprecise result. Okay, letter B is an imprecise archery but an accurate archery. C is precise but not accurate. D is precise and accurate. So you will notice here that in this direction, so according to increasing accuracy, the direction for this illustration is this. This is your increasing accuracy. And as you predicted, this will be your increasing precision. So in other words, let's say A is inaccurate and imprecise, B is accurate but imprecise, C is precise but inaccurate, and D is precise and accurate. So you will notice here, if this is your true value, if the center is your true value, accuracy pertains to how consistent your measurements are with respect to your target, like this one. Okay? Whereas for precision tells you how far your target is from your measurements. Okay, so in short, precision refers to consistency. Okay, accuracy pertains to correctness. Okay, sometimes we call this your bias. Okay, we call your precision uncertainty. So from these terms, we can see that A and C are biased. And that bias is usually a constant value away from your target. So if you're going to average these targets, okay, it looks like the average will be somewhere here. we're going to average all of these points, including here. So the distance from this average to your target is your bias. And that is easily corrected. If you know the bias, then you can just subtract your measurements with the bias, or you subtract your bias from the measurements, and you're just going to place all these points towards the center. Okay? Now, for consistency or for precision, we call this your uncertainty. Sometimes we call this your how spread your values are. So the more spread your values are, the less precise you are, just like A and B. Whereas C and D, okay, the measurements are close to each other regardless of your target measurement. So just to give you an idea, based on your experience from your laboratory experiment, the accuracy usually pertains to your percent error, because you're comparing this with a measured value with your true value. So this is the difference. So this is the difference. Divided by, of course, your true value. So you're comparing this, your measured value from the true value. And then, of course, that's 100%. Whereas, another, so to speak, error that you use is what we call your percent difference, wherein you compare two measurements, you compare two measurements, say measured value 1 minus measured value 2 divided by the average of the two measurements. And then multiply it by 100%. Okay? So in other words, your precision is measured by by looking at the differences of your measurement, regardless of whether your measurements are near to an actual value. We usually use percent difference in your laboratory experiments when you don't know the actual value. But if you know the actual value, we use percent error, because we want to know how accurate our measured value is from the true value. Percent difference tells you what would be the degree of differences of your measurements. Am I making sense?
Sir.
Okay. So again, as I mentioned before, a numerical method should be sufficiently accurate. Okay, it should be sufficiently accurate or unbiased to meet the requirements of a particular problem. Also, your numerical methods or the results for your numerical method should be precise enough for adequate design. Okay, so while these are useful to some extent, these percent errors to some extent, so let's make a formal enumeration of certain errors that we're going to use in this class. So number one is your we call the absolute error or numerical error. Or sometimes we call this your numerical error. Going to see our earlier graph. Okay, the true error would be just the true error or numerical error. Let's call this ET. Will just be the difference between the true value and your approximation. So in this case, we're looking at this let's say, difference. Okay? This is your true value. That's why it's called ET, true error, or absolute error, or numerical error. Now, the problem here is you can have the same true error, but in the context of what you're measuring, that same value can be insignificant to one, but significant to the other. So, for example, we are measuring, let's say, you're measuring the length of this joint bracket. So you're measuring this joint bracket. And then let's say you're measuring the length of a bridge. So let's call this L1 and L2. And let's say, for example, that you measure the length of the bracket to be, when you did your measurement, let's say 9 centimeters. But L2, which is the length of the bridge, you measured it by with the length of 9,999 centimeters. Now, if the true value of your length, let's call this L1T, is the true length of L1 is 10 centimeters, and the true length of your bridge, this bridge segment, is, let's say, 100 meters or 10,000 centimeters, you will see that both their error is 1 centimeter. You see, you have the same absolute error, 1 centimeter. But as you notice, this 1 centimeter is immaterial if you're going to consider the length of a bridge. This is nothing compared to the length of the bridge. But this is significant to the length of your bracket. You see the difference? You see the problem? So, that's why, while sometimes we determining the true value or the true error is enough, sometimes we have to normalize the error with respect to the true values. So that's why we define a new kind of error called the relative error. Wherein the relative error is actually let's call this epsilon t. So this is your true value minus your approximation, and then you divide it with the true value. So what we're doing here is we're actually normalizing. Sometimes we call this this is actually your percent error. Okay, so this is your true percent relative error, and then what's here, this is actually your true fractional error. Okay, you just multiply it by 100% to get the relative error. So again, this is also known as your true percent relative error. Okay, so there are two things that you need to know. in order to determine the true relative error, you have to know the true value. So in our case here, that's our analytical or exact solution, and an approximation, which is determined using your numerical methods, the red one. Okay, so from our example earlier, this 1 centimeter, the relative error for the bracket, would be what? This is 1 centimeter divided by 10 centimeter. So this is what? 10%. Whereas the relative error or percent relative error for the bridge is what? This is 0.1. That's 1 centimeter divided by 10,000 times 100. So that's 0.01%. So we have the same true error, but the relatively, this error is immaterial or is not significant when we're dealing with the bridge, but it's significant when we're dealing with the joint bracket. Okay? Now, the problem with relative error is usually, especially in real-world applications, we don't know the true value. That's why we're doing measurements. Okay? So most of the time we're not doing any, we do not know the true value. Sometimes we call it your a priori value. So therefore we express or we define another kind of error, and we call it your approximate relative error, or this is approximate relative error. Sometimes this is your percent relative error. So what we do here is we normalize the error using the best available estimate of the true value, which is an approximation itself. Okay, so to calculate this, let's call this epsilon A for approximate. So what we have here is we have a present measurement or approximation, and then we compared it with a previous approximation. And then we compared, and then we divide it, we normalize it with the present approximation. So in this case, we consider the present approximation to be the best available estimate of the true value. Of course, we multiply this with by 100%. Okay, so what we do is you have let's say value number 1, and then we use this value number 1 to estimate value number 2. We're measuring the same thing, okay? And we compared it with the first value, the previous value, and then we come out with an estimate. Now, if this is low enough, we check this one, and then for that, so again we have a previous approximation. Usually we have this is not that accurate, but when you do the computation later, we'll do some kind of this kind of solution. So you have a previous approximation, and then you have a new approximation, Sometimes this new approximation is dependent on your previous approximation, just like what we did here. So when we compare this, and then we come up with a relative error. Then we do the same. We make another measurement, let's say a third value, and then this third value is compared to your previous value, and then we come up with another approximation. Let's check. Now the question is, this iteration can go on forever. So there must be a stopping criteria. Okay? So how do you know your stopping criteria? How do you know if your present approximation is good enough? So we should define some kind of a error tolerance. What error, how much error do you want to tolerate? Tolerance. Okay, so we call this epsilon s, wherein s is used as a stopping criteria. You can define it yourself. For example, for a series of measurements, you want to stop at, let's say, 1%. So remember your assignment before in Physics 116 and in Theoretical Mechanics 1 when I asked you to up to what angle is your small angular approximation sine theta approximately equal to theta is valid. And then I say up to 1% error. So remember that? So what we did here is, this is actually your stopping criteria. Okay, so you list down the sine theta here, and then you list down your theta here, of course, in radians, and then you compute for the percent error. Then you see, where do you stop? That's your stopping criteria. Okay, of course, you can set this anytime you want, but there is a systematic way to determine the error tolerance. And this is given by this equation. The error tolerance is equal to 0.5 times 10 to the 2 minus n %. This is provided by a paper in 1966 by Scarborough. This is not the shoal. Okay. So what does this mean? Okay, this is set so that we can be assured that the result is correct to at least n significant figure. So this n significant figure is the number of significant figures after the decimal place. Okay,